Tonight, we're going to imagine something that sounds like a dream but hides a nightmare inside it. A space habitat, drifting through deep space, far from any star, any planet, any hope of rescue. Inside, the air feels clean, the lights are steady, the walls hold firm against the vacuum. It looks like a home, but it is not a home. It is a machine. Every breath the people inside take exists because a pump is running. Every drop of water they drink has been filtered from their own sweat and urine. Every degree of warmth comes from a reactor that must never stop. And tonight, we're going to find out how long that machine can keep pretending to be a world before the pretending fails. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Are you comfortable? Now, let's begin. Imagine you are standing in a corridor. The floor beneath your feet is smooth metal with a faint rubberized grip. The lighting overhead is warm, not the harsh fluorescent white you might expect, but something tuned to resemble late afternoon sunlight. The air smells faintly of humidity and green things. Somewhere nearby, you can hear the low hum of ventilation fans, steady and even, the kind of sound that becomes invisible after a few hours because your brain stops registering it. There is a window to your left, and through it you can see a garden, not a large one. A room perhaps 10 meters long and 6 meters wide, filled with trays of leafy greens under panels of soft pink and blue grow lights. The plants are healthy. They are producing oxygen. Someone has watered them recently. Everything feels calm. If you turn around and walk the other direction, you pass through a common area with a table bolted to the floor and chairs designed to stay in place. There are personal touches. A photograph pinned to a small board, a hand-drawn calendar with days crossed off, a book with a cracked spine sitting on a shelf that has a lip to keep things from floating away. Though here, in this habitat, things do not float. There is gravity, or something close enough to it. The floor pushes against your feet the way a floor should. You can set a cup of water down and it stays. Beyond the common area, there are sleeping quarters. Small, private, each one just large enough for a bed, a narrow desk, and a storage compartment. Farther on, a medical bay with equipment that would not look out of place in a well-stocked rural clinic. Exercise machines, a workshop with tools mounted on magnetic strips, a water recycling station behind a sealed panel, quietly processing the moisture from every breath and every shower into something drinkable. It feels like a place, a small place, a cramped place, but a place where people live. You could almost forget where you are. Almost. But then you notice something. There are no windows to the outside. Not one. The garden window is an interior window, looking from one pressurized room into another. Every wall around you is a wall between you and the void. And when you press your hand flat against the outermost wall of the corridor, the one that faces space, the metal is cold. Not dangerously cold. The insulation is working, but cold enough that you can feel the truth through your fingertips. On the other side of this wall, the temperature is approximately minus 270 degrees Celsius. That is 3 degrees above absolute zero. The point where molecular motion nearly stops. The point where unprotected human tissue freezes solid in seconds. And the air you are breathing. It is not coming from outside. There is no outside. Not in any sense that matters. The nearest planetary atmosphere is hundreds of millions of miles away, possibly billions. The oxygen in your lungs was generated by a machine that splits water molecules using electricity, or it was exhaled by the plants in that small garden you walk past. Plants that are alive only because other machines provide them with light, water, nutrients, and a stable temperature. The carbon dioxide you just breathed out is already being captured by a chemical scrubber somewhere in the ventilation system, pulled from the air before it can accumulate to levels that would give you a headache, then confusion, then death. The gravity you feel under your feet is not gravity. It is centrifugal acceleration, produced by the slow rotation of the habitat around its central axis. If the rotation stopped, you would float. Your muscles, calibrated to push against the floor, would find nothing to push against. The water in your cup would drift into a shimmering sphere. The carefully arranged garden trays would lift off their mounts. Everything that feels normal, every physical interaction that your body interprets as stable and safe, is a product of engineering. It is manufactured normalcy, and it requires a machine to keep spinning. This is a deep space habitat, and nothing about it is natural. The distinction matters because the words we use shape how we think about things. When someone says habitat, the brain reaches for associations. A habitat is where an animal lives. A habitat is a place suited to life. The word carries an implication of belonging, of a natural fit between the organism and its environment. But a deep space habitat is the opposite of that. It is an environment that is fundamentally hostile to human life, held at bay by layers of engineering, every one of which must function continuously. The word habitat is a courtesy. The accurate term would be something closer to life support vessel, or pressurized survival enclosure, or the machine that keeps you from dying. And this distinction becomes critical when you ask the question at the center of tonight's episode. How long could one of these things actually last? Not how long could people survive inside it, though that matters. The deeper question is how long the habitat itself, the structure, the systems, the interconnected web of mechanical and biological processes that create breathable air and drinkable water inside a metal shell surrounded by nothing, how long could all of that keep working? Because the moment it stops working, the people inside do not get to call for help. They do not get to step outside and wait for a repair crew. They do not get to open a window. There is no window. There is no outside. There is the habitat, and there is death. And the boundary between them is the thickness of a wall and the reliability of a pump. Let us be precise about what a deep space habitat is and what it is not, because the concept gets confused with several related ideas that work very differently. A spacecraft is a vehicle. It carries people from one place to another. It is designed for a journey with a defined start and end. The crew aboard a spacecraft is in transit. They are going somewhere, and when they arrive, they leave the vehicle. The life support requirements of a spacecraft are bounded by the duration of the trip. If the journey is 6 months, the spacecraft needs to sustain its crew for 6 months. It can carry consumables for that period. It can accept a certain level of system degradation because the mission ends before the degradation becomes critical. A space station in low Earth orbit, like the International Space Station, operates under a completely different set of assumptions. The ISS is remarkable. It has been continuously inhabited since the year 2000, supporting crews of up to 13 people at a time, maintaining breathable atmosphere, drinkable water, and a functional working environment in the vacuum of space for over 25 years. But the ISS is not self-sufficient. It is not even close to self-sufficient. It receives regular resupply missions from Earth, roughly every few weeks, delivering food, water, spare parts, replacement hardware, scientific equipment, and personal supplies. When a critical component fails on the ISS, a replacement can be launched from Earth and delivered within weeks or months. When the carbon dioxide removal system malfunctions, engineers in Houston can talk the crew through a repair in real time. Because the communication delay between the station and mission control is less than 1 second. When something goes seriously wrong, an evacuation vehicle, a Soyuz capsule, or a Crew Dragon is docked at the station at all times, ready to bring the crew home in hours. A deep space habitat has none of these advantages. No resupply, no rapid communication, no evacuation option, no Earth below, close enough to reach in an emergency. The habitat is alone in the most absolute sense the word allows. A planetary base on the Moon or Mars is closer to a deep space habitat in some ways, but fundamentally different in others. A base on a planetary surface has the ground beneath it. It has local resources that can potentially be extracted and used, water ice in lunar craters, carbon dioxide in the Martian atmosphere, regolith that can be processed into building materials. It has a gravitational field provided by the body it sits on, not manufactured by rotation. It has a horizon, a landscape, geological stability beneath its foundations, and the psychological benefit of being on something rather than in the middle of nothing. A planetary base faces enormous challenges of its own, but it is not floating in a void with no external reference point and no material resource other than what it brought with it. A deep space habitat is none of these things. It is a sealed vessel, pressurized, insulated, shielded, powered, and maintained entirely from within, located in a region of space where the nearest solid body might be millions or billions of miles away. It could be drifting between planets. It could be positioned at a gravitationally stable point far from any world. It could be in transit through interstellar space. The specific location matters less than the defining condition. There is nothing nearby. No ground, no atmosphere, no magnetic field, no resupply route, no communication relay that does not involve significant delay, and no rescue vehicle that could arrive in time to matter if something goes critically wrong. That is the scenario we are investigating tonight. Not a space station with a lifeline to Earth. Not a colony on Mars with local resources. Not a generation ship, which is a different problem explored in a different episode. A deep space habitat. Sealed. Alone. Dependent entirely on the system's inside its walls for every condition necessary to sustain human life. And those systems are more numerous and more interdependent than most people realize. Start with the most basic requirement: pressure. Human beings need atmospheric pressure to survive. On Earth, at sea level, the atmosphere exerts a pressure of approximately 14.7 pounds per square inch on every surface, including your body. You do not feel it because your internal pressure matches. Your lungs, your blood vessels, your cells, all of them are calibrated to operate at this pressure. Remove it, and the consequences are immediate and catastrophic. In a vacuum, the moisture on your tongue and in your lungs begins to boil, not because it is hot, but because the boiling point of water drops as pressure decreases. Gases dissolved in your blood begin to come out of solution, forming bubbles. Consciousness is lost within 10 to 15 seconds. Death follows within 1 to 2 minutes. A deep space habitat must maintain internal pressure at or near Earth sea level values. roughly 1 atmosphere, against an external pressure of 0. This means the hull is a pressure vessel, like a balloon inflated in a vacuum, constantly under stress. Every wall, every joint, every seal, every window, every hatch, every penetration point where a cable or pipe passes through the hull is a potential failure point. A pressure vessel does not need a dramatic impact to fail. A microscopic crack in a weld, a seal that has dried out and lost elasticity over years, a thermal stress fracture in a hull panel that has expanded and contracted through thousands of temperature cycles. Any of these can produce a slow leak, and a slow leak in a sealed habitat is not a minor inconvenience. It is a countdown. On the ISS, small pressure leaks have occurred multiple times. In 2018, a slow leak was detected at the Soyuz capsule docked to the station, caused by a small hole approximately 2 millimeters in diameter. The crew patched it with epoxy and a gauze seal. In 2020, a persistent air leak was traced to a crack in the Zvezda service module, one of the oldest components of the station. The leak was slow enough that it did not pose an immediate danger, but it required ongoing monitoring and repeated repair attempts over months. These incidents were manageable because the ISS had resupply capability, communication with ground engineers, and the ability to isolate sections of the station while repairs were made. In a deep space habitat, a pressure leak that cannot be found and permanently repaired is an existential threat. Every cubic meter of air that escapes is air that has to be replaced. And in a sealed system, replacement air comes from reserves that are finite. The habitat's atmosphere is not being topped off from outside. It is a closed inventory. Every molecule of nitrogen and oxygen inside the hull at launch is, in principle, every molecule of nitrogen and oxygen the habitat will ever have. Lose enough of it, and the pressure drops. When the pressure drops, the systems designed to operate at 1 atmosphere begin to perform differently. Boiling points change, evaporation rates change, the efficiency of water recycling equipment shifts. The plants in the agricultural section respond to altered atmospheric pressure in ways that affect their growth rates and gas exchange. A slow leak does not just reduce the air supply. It destabilizes every process calibrated to operate at normal pressure. And pressure is only the beginning. The air inside the habitat has to be actively managed in its composition, not just its pressure. Human beings inhale air that is roughly 21% oxygen and exhale air that is roughly 16% oxygen and 4% carbon dioxide. In an enclosed space, carbon dioxide accumulates. At concentrations above 1%, headaches and drowsiness begin. Above 5%, judgment is impaired and breathing becomes labored. Above 10%, unconsciousness and death follow. Even below those acute thresholds, chronic exposure to mildly elevated carbon dioxide, above 0.5%, has been shown to impair cognitive function in ways that are measurable on testing, but not always obvious to the person affected. They think more slowly. They make more errors. They do not realize it is happening. The habitat needs a system that continuously removes carbon dioxide from the air and either stores it, vents it, or converts it back into something useful. On the ISS, the carbon dioxide removal assembly uses beds of zeolite, a porous mineral that adsorbs carbon dioxide when exposed to cabin air and releases it when heated. The system alternates between 2 beds, one adsorbing while the other regenerates. It works, but it requires continuous maintenance, periodic replacement of components, and engineering support from ground teams when problems arise. It is one of the most maintenance-intensive systems on the station, and its reliable operation depends on a support infrastructure that a deep space habitat would not have. A deep space habitat cannot call Houston when the carbon dioxide scrubber malfunctions. The crew must diagnose the problem, identify the failed component, locate a replacement if one exists, and perform the repair, all while the carbon dioxide level in the air they are breathing is rising. If the repair takes too long, or if the replacement part does not exist, the crew begins to experience the symptoms of carbon dioxide poisoning while trying to fix the machine that is supposed to prevent carbon dioxide poisoning. This is not a hypothetical scenario. It is a predictable consequence of operating complex mechanical systems without external support. Oxygen has to be generated. On the ISS, the oxygen generation assembly produces oxygen by splitting water molecules into hydrogen and oxygen through electrolysis. The oxygen is released into the cabin air. The hydrogen is either vented or fed into the Sabatier reactor, which combines it with carbon dioxide to produce water and methane, partially closing the loop. This system requires electricity, clean water, and functioning hardware. If the electrolysis unit fails, backup oxygen is available from pressurized tanks. But those tanks are finite. They buy time. They do not solve the problem. Water must be recycled. On the ISS, the water recovery system collects humidity from the cabin air, processes wastewater, and reclaims water from crew urine through a distillation and filtration process. The current system achieves a recovery rate of approximately 98%. A milestone reached in 2023 with the addition of a brine processor that extracts the last usable water from the concentrated urine brine. 98% sounds nearly perfect. But think about what 2% loss means over time. If the habitat processes 100 liters of water per day, 2 liters are lost every day. Over a year, that is 730 liters gone. Over 5 years, 3,650 liters. Over 10 years, more than 7,000 liters. Irreplaceable unless the habitat has reserves large enough to buffer that loss, or a way to recover the final 2%. And 2% is the best case number. Any degradation in the filtration membranes, any fouling in the distillation hardware, any failure in the brine processor, and the recovery rate drops. 3% loss, 4% loss. The numbers sound small. The water disappearing is not small. It is the water you are going to drink next year. Food must be grown, not delivered, not unpacked from a cargo module. Grown inside the habitat, under artificial light, in soil or hydroponic solution, using water that was recycled from the last crop and nutrients recovered from composted waste. A single person requires roughly 2,000 calories per day. Producing that many calories from crops grown under artificial lighting requires significant growing area, significant electrical power for the lights, and a functioning agricultural ecosystem that must remain stable across seasons and years. Crop failures happen on Earth with all the resources of an open environment and a global agricultural supply chain. In a sealed habitat, a crop failure is not an economic loss. It is a food emergency. Power must be generated. Every system described above, pressure maintenance, atmosphere management, water recycling, food production lighting, thermal control, runs on electricity. The most credible power source for a deep space habitat is nuclear fission. A well-designed fission reactor using enriched uranium or thorium can operate for years, potentially decades, without refueling. But the reactor requires cooling, shielding, maintenance, and monitoring. It produces heat that must be managed. It generates radioactive waste that must be contained. Its control systems require functioning electronics that are themselves subject to degradation from the radiation the reactor produces. The reactor is the heart of the habitat. Everything else depends on it. And if it fails, everything else follows. Not immediately, but soon. Battery reserves might sustain critical systems for hours or days, but without primary power, the habitat is dying. Temperature must be controlled. This is a challenge that surprises people because space seems cold, and it is cold. The background temperature of deep space is roughly minus 270 degrees Celsius. But the problem is not just keeping warm, it is managing heat. Every running system inside the habitat generates heat. The reactor generates heat. The lights generate heat. The computers generate heat. The human bodies generate heat, roughly 100 watts per person at rest, more during exercise. In a sealed, insulated structure, that heat accumulates. On Earth, you open a window. In space, there is no window, no breeze, no atmosphere to carry heat away. The habitat must radiate excess heat into space using large panels called radiators that emit thermal energy as infrared radiation. If the radiators degrade, if they lose surface area to micrometeoroid damage, if their thermal coatings break down, the habitat gets warmer, slowly, a fraction of a degree at a time. But the direction is wrong, and the trend does not reverse itself, and waste must be processed. Every biological process produces waste. Human metabolism produces carbon dioxide, water vapor, urine, feces, and heat. Food production produces plant waste, inedible biomass, and spent growth media. Equipment maintenance produces worn parts, used filters, contaminated fluids. In an open environment, waste disperses. In a sealed habitat, waste accumulates. If it is not processed, broken down, sterilized, and recycled back into the system, it becomes a contamination source, a disease vector, and a chemical hazard. The habitat's waste management system is not an afterthought. It is as critical as the oxygen generator, because a habitat that cannot process its waste is a habitat that is slowly poisoning itself. Every one of these systems is connected to every other system. The oxygen generator needs water and electricity. The water recycler needs electricity and functioning filters. The filters need to be manufactured or replaced from spares. The spares need storage space and an inventory management system. The electricity comes from the reactor. The reactor needs cooling. The cooling system needs functional radiators. The radiators need intact surfaces. The surfaces degrade under micrometeoroid bombardment. The repair of the surfaces requires materials and tools and a crew member who knows how to perform the repair, and is not currently occupied fixing the carbon dioxide scrubber that broke down this morning. This is the reality of a deep space habitat. Not a home with a view of the stars, not a cozy shelter floating in the gentle dark. It is a web of interdependent mechanical and biological systems, each one essential, each one fragile in its own way, each one connected to the others by dependencies that mean a failure in one place can cascade into failures somewhere else entirely. And all of it, every pump, every valve, every filter, every seal, every wire, every bearing, every reactor control rod, every square meter of radiator surface, all of it is surrounded by an environment that will kill every person inside within minutes if the systems stop doing their jobs. That is what the word habitat is hiding. And that is what we need to understand before we can answer how long one could survive. Because survival, in this context, does not mean that the people inside are alive. It means that the machine that keeps them alive is still functioning, still pressurized, still generating power, still recycling air and water, still holding back the vacuum, still managing its own heat, still repairing itself faster than it is breaking down. The moment the balance tips, the moment the habitat begins degrading faster than it can be maintained, the clock starts. And in deep space, there is no one coming to reset it. What keeps that balance from tipping is the subject of what comes next. We need to go deeper into each of these systems, not as abstractions on a diagram, but as physical machines with physical parts that wear out, break down, clog, corrode, overheat, and fail. Because the question of how long a habitat survives is not answered by the best case performance of its systems on day one. It is answered by what happens to those systems on day 1000, and day 10,000, and the day after the last spare part is used. There is a concept in engineering that does not get talked about enough outside of technical circles. It is called maintenance burden. It refers to the total amount of human labor, spare parts, diagnostic effort, and operational time required to keep a system functioning across its intended lifespan. For a car, the maintenance burden is manageable. You change the oil, replace the brake pads, rotate the tires, and occasionally deal with something unexpected. If a repair exceeds your capability, you take the car to a mechanic. If the car breaks down beyond repair, you buy another one. For a deep space habitat, the maintenance burden is the entire point. The habitat does not drive somewhere and park. It does not get dropped off for service. It does not get replaced. Every system inside it must be maintained by the people who depend on it for survival, using only the tools and materials the habitat carries, for as long as the habitat is expected to operate. The maintenance burden is not a background task. It is the primary occupation of everyone aboard. Growing food, recycling water, scrubbing the air, monitoring pressure, inspecting seals, calibrating instruments, repairing equipment. These are not chores performed between other activities. They are the activity. The habitat does not exist to let people do something else. The habitat exists to keep people alive, and keeping people alive is a full-time job for the people being kept alive. Let us look at what that job actually involves, system by system, in the specific mechanical detail that determines whether the habitat survives or does not survive. Atmosphere management is where the maintenance burden first becomes visible, because the air inside a sealed habitat is not stable. It is constantly shifting. Humans consume oxygen and produce carbon dioxide, but they also produce other things. Sweat evaporates, adding moisture to the air. Skin cells shed. Cooking releases volatile organic compounds. Cleaning solvents off-gas. Equipment lubricants slowly evaporate. Plastics and adhesives release formaldehyde and other chemicals in trace amounts over months and years. The air inside a sealed habitat is not simply a mix of oxygen and nitrogen. It is a soup of hundreds of trace gases, each present in tiny concentrations, most of them harmless individually, some of them accumulating to problematic levels over time if they are not actively removed. On the ISS, a system called the Trace Contaminant Control System handles this. It uses activated charcoal beds to adsorb volatile organic compounds and a catalytic oxidizer to break down certain contaminants at high temperature. The charcoal beds eventually saturate and need replacement. The catalytic oxidizer requires a specific operating temperature and periodic recalibration. Both systems consume power and require spare components. On the ISS, Replacement charcoal canisters are delivered from Earth. In a deep space habitat, every canister the habitat will ever use must be aboard from the start, or the habitat must have the ability to regenerate the charcoal somehow, which requires additional equipment, energy, and expertise. And the atmosphere system does not just remove bad things, it must actively produce the right things. Oxygen generation through electrolysis, splitting water into hydrogen and oxygen, is the most reliable method, but it is not without complications. The electrolysis cells contain membranes and electrodes that degrade over time. The hydrogen produced as a byproduct must be managed. If it is vented, the habitat loses hydrogen atoms that were originally part of its water supply, meaning the water inventory shrinks with every oxygen cycle. If the hydrogen is fed into a Sabatier reactor to combine with carbon dioxide and produce water and methane, that closes part of the loop. But the reactor itself is another piece of hardware with its own maintenance requirements, its own failure modes, and its own need for spare parts. The ISS oxygen generation assembly has experienced multiple failures during its operational life, including issues with hydrogen sensors, firmware glitches in control software, and degradation of its internal components due to the chemistry of the electrolysis process itself. Each failure required troubleshooting, sometimes taking days to diagnose and repair, with mission control providing step-by-step guidance to the crew. In a deep space habitat, that guidance does not arrive in real time. A signal sent to Earth from beyond the orbit of Mars takes between 4 and 24 minutes to arrive, depending on orbital positions. From the outer solar system, it takes hours. From true interstellar distances, it takes years. The crew must diagnose and fix the oxygen generator themselves, using whatever documentation, training, and institutional knowledge they carry. And they must do it while the oxygen level in the cabin air is dropping. Carbon dioxide removal is equally fragile. The zeolite-based scrubbing systems used on the ISS work by cycling between two beds, one adsorbing carbon dioxide from the air, while the other is heated to release its captured carbon dioxide into space or into a processing system. This cycling requires precise timing, functioning valves, and consistent airflow. Documented problems on the ISS include valves that stick in the wrong position, zeolite beds that become contaminated by humidity and lose adsorption capacity, and timing instabilities that cause one bed to saturate before the other is ready. These are not catastrophic failures. They are the kind of incremental degradation that complex mechanical systems experience as a matter of course. On the ISS, the consequence is a temporary rise in cabin carbon dioxide, a headache for the crew, and a call to Houston. In a deep space habitat, the consequence is a crew that is slowly being poisoned while trying to repair the machine that is supposed to prevent exactly that. Now consider water. We talked about the overall recovery rate, approximately 98% on the ISS as of 2023. But the mechanical reality behind that number is far more complex than a single percentage suggests. The water recycling system is not one machine. It is a chain of machines, each performing a different step in the process. The urine processor assembly heats urine under low pressure, causing the water to evaporate and separate from the dissolved solids. The vapor is condensed and sent to the water processor assembly, which runs the water through a series of filters, including particulate filters, ion exchange beds, and a catalytic reactor that breaks down organic contaminants. The output is potable water that meets standards stricter than most municipal water on Earth. Each step in this chain has components that degrade, filters clog, ion exchange beds exhaust their capacity. The catalytic reactor eventually loses efficiency. The distillation unit in the urine processor has experienced problems with calcium sulfate precipitation, a mineral crust that forms when calcium in the urine reacts with sulfuric acid used in the pre-treatment process. This precipitation fouled the distillation hardware, reduced the water recovery rate from the design target of 85% to approximately 74% for a period, and required a reformulation of the pre-treatment chemistry using phosphoric acid instead of sulfuric acid. That reformulation was developed on Earth, tested in laboratories, and then implemented on the ISS. In a deep space habitat, when an unexpected chemical reaction fouls the water processor, who develops the fix? The crew aboard the habitat are trained operators and skilled technicians. Some may have backgrounds in chemistry or chemical engineering, but developing a new pre-treatment formula for a urine processing system is research work that on Earth involved laboratories, multiple iterations, controlled testing, and peer review. The habitat must either carry enough chemical diversity and laboratory capability to perform this kind of troubleshooting independently, or it must accept that certain failure modes will reduce system performance permanently. And even when the system works as designed, there is the issue of biological contamination within the water lines themselves. Biofilms, thin layers of microbial growth, form on the interior surfaces of pipes, tanks, and filter housings wherever water flows. These biofilms are extraordinarily difficult to eliminate in a running system, because you cannot disassemble and sterilize the entire water infrastructure without shutting down the water supply. On Earth, municipal water systems manage biofilms through chlorination and periodic flushing. On the ISS, iodine or silver ions are added to the water as biocides, but biofilm formation is an ongoing challenge. Over years and decades, biofilm accumulation in a deep space habitat's water system could compromise water quality, clog narrow passages, and seed microbial contamination into parts of the system that were designed to remain sterile. This is not a dramatic failure. It is a slow fouling, a gradual thickening of microbial mats on surfaces the crew cannot see and may not be able to reach. Food production deserves a much deeper examination than most discussions of space habitats provide, because it is the point where engineering meets biology in the most unpredictable way. Growing enough food to sustain a crew of even 6 to 10 people requires substantial growing area, substantial lighting energy, and a functioning ecosystem of soil microorganisms, nutrient cycles, and plant physiology. Hydroponic systems, where plants grow in nutrient-rich water rather than soil, are more space efficient. Aeroponic systems, where roots hang in air and are misted with nutrient solution, use even less water. Both approaches have been tested on the ISS and in ground-based analogs. They work. Lettuce, radishes, wheat, and other crops have been grown successfully in controlled environments. But growing a few heads of lettuce for supplemental nutrition is a different challenge from growing the entire caloric intake of a human crew for years. A single person needs roughly 2,000 calories per day. Producing that many calories from plants requires approximately 40 to 50 square meters of growing area per person, depending on the crop mix, the light intensity, and the efficiency of the agricultural system. For a crew of 8, that is 320 to 400 square meters of active growing space more than 3,000 square feet, all of it requiring artificial lighting, irrigation, nutrient management, pest monitoring, and harvest labor. And the crops must be diverse. A viable diet requires grains for caloric density, legumes for protein, root vegetables for carbohydrates, leafy greens for vitamins and minerals, and ideally some source of fats and additional protein. Wheat, rice, soybeans, potatoes, sweet potatoes, and peanuts are among the most studied crops for closed system agriculture. Each has different lighting requirements, different growth cycles, different susceptibility to disease, and different nutrient demands. Managing a multi-crop agricultural system in a sealed environment is not farming in any traditional sense. It is applied ecology under extreme constraints, and it must work every single growing cycle without significant failure. Because the margin between adequate nutrition and hunger in a closed system is thin. This is where the lessons of Biosphere 2 become directly relevant, and those lessons are sobering. Biosphere 2 was a sealed ecological facility built in the Arizona desert, covering an area of approximately 13,000 square meters, containing multiple biomes including a rainforest, an ocean, a savanna, a marsh, a desert, and an agricultural zone. 8 people sealed themselves inside in September of 1991, intending to live for 2 years entirely on what the closed system could provide. The agricultural system worked, barely. The crew grew approximately 80% of their food, supplemented by stored seed stocks. They were hungry for most of the 2 years, losing an average of 16% of their body weight. But the more alarming problem was the atmosphere. Oxygen levels began dropping almost immediately after the facility was sealed. Over the first 16 months, the oxygen concentration fell from the normal 21% to approximately 14%, equivalent to the oxygen level at an altitude of roughly 4,300 meters, comparable to the summit of many serious mountains. The crew experienced fatigue, impaired judgment, difficulty sleeping, and a reduced physical capacity. Carbon dioxide levels fluctuated in ways that were difficult to predict or control. The cause was eventually identified. The soil in the agricultural and biome areas contained large amounts of organic matter. Microbes in the soil were consuming oxygen as they decomposed this organic material, producing carbon dioxide. The rate of microbial oxygen consumption exceeded the rate at which the plants could replace it through photosynthesis. The system was out of balance, and the imbalance was driven by a biological process that the designers had underestimated, because no model of a complex soil ecosystem captures every variable. Supplemental oxygen was pumped in from outside in January of 1993. This broke the seal of the closed system and was widely reported as a failure. But the more important lesson was not that the project failed. The lesson was that it revealed how much we do not understand about closed biological systems. The oxygen crisis was not caused by a mechanical breakdown. No pump failed, no valve leaked. The system was doing exactly what the biology dictated. The problem was that the biology did something the engineers did not predict. A deep space habitat that relies on biological life support, plants for oxygen, microbes for nutrient recycling, soil or hydroponic systems for food production, is inheriting this same fundamental uncertainty. Biological systems are not machines. They do not follow a maintenance schedule. They respond to conditions in non-linear ways. A change in temperature, humidity, light spectrum, or nutrient concentration can shift the metabolic output of a soil microbiome in ways that alter the entire atmospheric chemistry of the habitat, and these shifts may not be immediately apparent. They may accumulate over weeks or months before someone notices that the oxygen level is lower than it should be, or that the carbon dioxide level is creeping upward, or that a crop that was producing reliably for 3 years has suddenly declined in yield because the microbial community in its growing medium has changed in response to a trace contaminant that entered the nutrient cycle 6 months ago. The Soviet BIOS, 3 experiments conducted between 1972 and 1984, tested closed ecological systems with crews of 2 to 3 people for periods of up to 6 months. These experiments achieved higher degrees of atmospheric closure than Biosphere 2, largely because they relied on dense algae cultures, primarily chlorella, as the primary oxygen source rather than diverse soil-based ecosystems. Algae are more controllable than soil. Their growth rate responds predictably to light intensity and nutrient availability. But feeding people entirely on algae is not viable. The diet is monotonous, nutritionally incomplete, and psychologically difficult to sustain over months and years. The BIOS 3 crews supplemented algae-based air regeneration with conventional crop agriculture for food, achieving partial closure but not full self-sufficiency. The experiments confirmed that closed-loop biological life support is possible in principle, but extremely difficult to maintain in practice, and that the difficulty increases with the complexity of the ecosystem and the duration of the closure. Power generation underlies every other system, and its failure mode is the most consequential because it is not gradual. When the reactor loses the ability to produce electricity, every electrically powered system in the habitat stops. The lights go out, the air scrubbers stop, the water pumps stop, the ventilation fans stop, which means carbon dioxide begins accumulating in whatever room the crew happens to be in, because without forced circulation, exhaled carbon dioxide settles around the breathing zone and does not mix with the broader cabin air. The electrolysis unit stops producing oxygen. The temperature control system stops managing heat. The habitat does not slowly wind down. It begins dying, on a timeline measured in hours for air quality and days for temperature. Nuclear fission reactors are the most credible power source for a deep space habitat because they offer the highest energy density in a form that does not depend on sunlight, does not require enormous fuel volumes, and can operate continuously for years. Modern naval reactors are the kind that power aircraft carriers and submarines routinely operate for 20 to 25 years between refueling. A habitat reactor might need to run longer than that, and it would need to do so without access to a shipyard for overhaul. The reactor's fuel elements gradually deplete as fissile material is consumed. Control rods, which regulate the nuclear reaction by absorbing neutrons, must move precisely in their guide channels. If a control rod mechanism develops excessive friction, or if a bearing in the drive system wears beyond tolerance, the reactor's power output becomes harder to regulate. The reactor coolant system, which carries heat from the reactor core to the power conversion equipment, and ultimately to the radiators that shed waste heat into space, circulates fluid through a closed loop of pipes, pumps, heat exchangers, and valves. Every component in that loop is subject to corrosion, erosion, and material fatigue over time. The coolant fluid itself can degrade, accumulating contaminants from the pipe walls that alter its thermal properties. The pumps that circulate the coolant have moving parts, bearings, and impellers that wear. If a coolant pump fails, The backup pump takes over, but now there is no backup for the backup. This layered redundancy is the habitat's primary defense against any single failure becoming a catastrophe. 2 oxygen generators, so that if one fails, the other can sustain the crew while repairs are made. 2 water recycling systems, 2 carbon dioxide scrubbers, backup batteries for temporary power loss, spare pumps, spare filters, spare valves. This redundancy is essential and effective, but it is not infinite. Each time a primary system fails and the backup takes over, the habitat has lost a layer of protection. If the backup also fails before the primary is repaired, the system is gone entirely. Redundancy buys time. It does not buy immortality. And there is a subtler problem with redundancy that engineers understand, but is rarely discussed outside technical literature. Backup systems that sit idle for long periods can fail when activated. Seals dry out, lubricants settle, valves stick in their last position. Electronics develop corrosion at contact points. A backup pump that has been sitting unused for 3 years may not start when the primary pump fails, because the very inactivity that preserved it from wear also allowed degradation from disuse. Prudent maintenance protocols require periodic activation and testing of backup systems, running them under load to verify they still function. This adds to the maintenance burden, the endless treadmill of inspection, testing, repair, and documentation that consumes the crew's working hours. Thermal control deserves deeper attention because its mechanics are counterintuitive. On Earth, heat management is straightforward. Hot things radiate, convect, and conduct heat into their surroundings. Air moves heat away from surfaces. Water absorbs and carries thermal energy. The atmosphere acts as a giant heat sink. In a vacuum, convection does not exist. There is no air to carry heat. Conduction requires physical contact between materials, and beyond the hole, there is nothing to make contact with. The only mechanism for shedding heat into space is radiation, the emission of infrared photons from a surface. The rate of radiative heat loss depends on the surface area of the radiator, the temperature of the radiator, and the emissivity of the radiator surface, a property that measures how efficiently a surface emits thermal radiation. A perfect emitter has an emissivity of 1. Real materials have emissivities less than 1, and those emissivities change over time as surfaces are degraded by radiation exposure, micrometeoroid impacts, and the slow accumulation of outgas contaminants from the habitat's own materials. A deep space habitat generating 50 to 100 kilowatts of electrical power from its reactor is also generating several hundred kilowatts of waste heat, because no power conversion system is perfectly efficient. That waste heat must be transported from the reactor and other heat-producing systems to the radiator panels, where it is emitted into space. The thermal management system includes fluid loops, heat exchangers, pumps, and the radiator panels themselves. If the radiators lose efficiency, whether through surface degradation, coolant contamination, or loss of surface area from impact damage, the habitat's internal temperature rises. Not dramatically at first, 1/10 of a degree per month perhaps, barely noticeable, but the direction is wrong, and over years, the cumulative effect changes the environment. Equipment runs hotter, electronics fail sooner. The crew is less comfortable, less alert, more prone to error. And the error they are most prone to making is the error of not noticing the slow change, because slow change is what humans are worst at detecting. Waste processing ties everything back together, because waste is not an endpoint. In a closed system, waste is a resource that has not yet been recycled. Human feces contain nitrogen, phosphorus, potassium, and organic carbon, all of which are essential nutrients for plant growth. Urine contains water, nitrogen, and trace minerals. Plant waste, stems, roots, inedible leaves, contains carbon and fiber that can be composted back into growing media. In principle, a well-designed habitat cycles these materials continuously, breaking down waste through biological or chemical processes and returning the constituent elements to the food production system. In practice, this cycling is imperfect. Composting requires specific temperature, moisture, and oxygen conditions. If the composting system overheats, the wrong microbes dominate and the process produces ammonia or hydrogen sulfide, both toxic in enclosed spaces. If the composting system is too cool, decomposition slows and waste accumulates faster than it is processed. If contaminants enter the composting stream, chemicals from equipment maintenance, cleaning agents, or pharmaceuticals excreted in urine, they can suppress the microbial community or introduce substances into the nutrient cycle that accumulate in food crops. And there is a class of waste that cannot be recycled at all with current technology. Worn mechanical parts made of specialized alloys, failed electronic components, degraded polymer seals and gaskets, spent chemical reagents. These materials accumulate as dead mass, taking up space, adding no value, and representing resources that were consumed and cannot be recovered. Over years, this dead mass grows. The habitat launched with a calculated inventory of materials, and every irreplaceable component that fails and cannot be recycled reduces the total resources available for the rest of the mission. This is the fundamental arithmetic of a closed system. Inputs are fixed at launch, outputs are zero. The only variable is how efficiently the habitat cycles its internal resources, and no cycle is 100% efficient. Every loop leaks. Water recycling loses 2% per cycle. Nutrient cycling loses trace elements to chemical dead ends. Air recycling loses atoms to side reactions and trace gas accumulation. Power generation consumes fuel. Structural materials fatigue. Filters exhaust. Seals age. Each of these losses is small. Individually, none of them is alarming. But they are all running simultaneously, and they are all running in the same direction. Toward depletion, toward degradation, toward a state in which the habitat has less of everything it needs, and less ability to compensate for what it has lost. The people inside the habitat experience this as an increasing maintenance burden. In the first year, the systems run close to their design specifications. Maintenance is routine, failures are rare and easily repaired from the supply of spares. In the third year, some components are on their second or third replacement cycle. The spares inventory is thinner. Certain repairs take longer because the remaining spares are not exact matches and require modification. In the fifth year, the first system that cannot be fully repaired is jury-rigged, a workaround that restores partial function, but at reduced efficiency. The crew adapts. They learn to live with a water recovery rate that has slipped from 98% to 94%. They adjust the crop rotation to compensate for a nutrient imbalance in the composting system. They run the backup carbon dioxide scrubber more frequently to make up for the primary unit's declining performance. Each adaptation is reasonable. Each workaround is clever. The crew is resourceful and trained and motivated. But each adaptation also means the habitat is operating further from its design baseline, with less margin for the next failure. And the next failure is coming, because the equipment is aging, and nothing aboard the habitat is getting younger or stronger or more reliable with time. This is the slow physics of a closed system, not an explosion, not a dramatic breach, a gradual tightening of margins, a slow erosion of capability, a patient accumulation of small losses that individually mean nothing and collectively mean everything. What makes this worse, what turns a manageable degradation into an existential problem, is what waits outside the whole. Because while the internal systems are quietly wearing down, the external environment is quietly working to accelerate that process. Radiation is damaging materials and human cells. Micrometeoroids are eroding the whole surface. Thermal cycling is fatiguing structural joints. And none of these external threats are optional. They are continuous, they are cumulative, and they do not care how well the crew is managing the systems inside. That is what we need to examine next. Not just what the habitat must do to stay alive, but what the universe is doing to make that job harder every single day. Everything we have discussed so far has been about the habitat's internal systems, the machines and biological processes that produce air, water, food, heat, and power inside the whole. If those systems were operating inside a gentle, stable, neutral environment, maintaining them would still be extraordinarily difficult. But a deep space habitat does not exist in a gentle environment. It exists in the most hostile environment human beings have ever tried to survive in. And that environment is not passive. It does not simply sit outside the hole and wait. It actively degrades the habitat, constantly, from every direction, through mechanisms that are invisible, silent, and relentless. The first and most pervasive of these mechanisms is radiation. On Earth, you are shielded from the radiation environment of space by 2 layers of protection so effective that most people never think about them. The first is Earth's magnetic field, a vast invisible bubble called the magnetosphere that deflects the majority of charged particles streaming through the solar system. The second is the atmosphere, roughly 100 kilometers of gas above your head that absorbs and scatters the particles and photons that make it past the magnetic field. Together with other natural sources like radon and terrestrial minerals, the total background radiation dose at Earth's surface is approximately 2 to 3 millisieverts per year, of which cosmic rays contribute less than half a millisievert. You receive these doses and they are biologically insignificant. A deep space habitat has neither of these shields. It sits in the unfiltered radiation environment of open space, exposed to everything the galaxy produces. And what the galaxy produces is formidable. Galactic cosmic rays are the primary concern for long-duration habitation. These are not rays in the traditional sense. They are particles, mostly protons and helium nuclei, but also heavier ions stripped of their electrons, accelerated to enormous energies by supernova remnants and other violent astrophysical processes across the galaxy. They arrive from every direction. They are constant. They do not come in bursts or storms. They are a steady rain of high-energy particles that permeates all of interstellar space and most of the solar system outside the protection of planetary magnetospheres. The energy of these particles is what makes them so dangerous and so difficult to shield against. A typical galactic cosmic ray proton carries billions of electron volts of energy, far more than any particle produced in normal chemistry. That energy is concentrated into a single nucleus moving at a substantial fraction of the speed of light. When such a particle strikes a material, it does not simply stop. It penetrates. It passes through centimeters or meters of material, depositing ionizing energy along its path. It breaks molecular bonds. It damages DNA. It shatters atomic nuclei in the shielding material itself, producing a spray of secondary particles, neutrons, protons, pions, and fragments of whatever nucleus was struck that radiate outward in all directions. This secondary radiation can be as biologically damaging as the primary particle, and in some shielding configurations, the total radiation dose behind the shield is actually higher than the dose without the shield, because the secondary particle shower adds more dose than the primary particle would have delivered on its own. This is the paradox of radiation shielding in deep space. Adding more material does not always help. For certain particle energies and certain shielding materials, particularly dense metals like aluminum, increasing the shielding thickness increases the secondary particle production without proportionally reducing the primary particle flux. The net effect is a higher dose behind the shield than in front of it. NASA research has shown that hydrogen-rich materials, particularly polyethylene and water, are more effective per unit mass than aluminum, because hydrogen nuclei, being single protons, produce fewer and lower energy secondary particles when struck. But even the best passive shielding materials cannot reduce the galactic cosmic ray dose to Earth surface levels without impractical amounts of mass. Current estimates suggest that behind approximately 20 grams per square centimeter of aluminum shielding, roughly the equivalent of the ISS hull thickness, an astronaut in deep space receives a radiation dose of approximately 1 to 2 millisieverts per day. That is roughly the annual background dose on Earth, received every single day. Over a year, the cumulative dose reaches 400 to 700 millisieverts, depending on solar activity. Over a decade, 4 to 7 sieverts. Career dose limits vary by agency. NASA's current limit is 600 millisieverts. The European Space Agency allows up to 1 sievert. A Habitat crew member would exceed even the more generous limit within 2 to 3 years. The biological consequences are cumulative and probabilistic. Radiation damages DNA. The body repairs most of this damage, but the repair is not perfect. Over years of exposure, the accumulated imperfect repairs increase the probability of cancer, cardiovascular disease, cataracts, and central nervous system effects, including cognitive decline. Studies using NASA's Galactic Cosmic Ray Simulator at Brookhaven National Laboratory have shown measurable effects on brain tissue, including inflammation, impaired synaptic function, and behavioral changes in animal models exposed to simulated deep space radiation environments. These effects are not acute. They do not announce themselves with immediate symptoms. They accumulate over years, quietly increasing health risks for every person inside the habitat. But radiation does not only damage human tissue, it damages everything. Polymer seals become brittle, lubricants break down, electronic components experience bit flips, and accumulated semiconductor damage. Optical surfaces darken. Structural composites lose strength as their polymer matrices are degraded by ionizing radiation. The very materials that make up the habitat are being slowly weakened by the same radiation that is slowly increasing the crew's cancer risk. The hull is getting weaker. The seals are getting less reliable. The electronics are getting less stable. And all of this is happening invisibly, at the molecular level, without any alarm or warning light. The second external threat is micrometeoroids. Deep space is not empty. It contains dust. Not the kind of dust you wipe off a shelf. Cosmic dust. Grains of rock metal and ice, ranging in size from fractions of a micrometer to several millimeters, distributed throughout the solar system and the interstellar medium. Most of these particles are extraordinarily small and pose no individual threat, but they are moving at extraordinary velocities relative to any habitat, typically between 10 and 70 kilometers per second within the solar system. At those speeds, kinetic energy is immense. A particle the mass of a grain of sand, roughly 1 milligram, traveling at 20 kilometers per second, carries kinetic energy equivalent to approximately 200 joules. That is roughly the energy of a bullet from a small caliber handgun, concentrated into a contact area smaller than a pinhead. The standard engineering response to this threat is the Whipple shield, first proposed by astronomer Fred Whipple in 1947. The concept is elegant. A thin bumper plate is mounted at a distance from the main hull. When a micrometeoroid strikes the bumper, the impact velocity is so high that both the particle and the bumper material at the impact site vaporize or fragment into a cloud of smaller, slower moving particles. This cloud then spreads as it crosses the gap between the bumper and the hull, distributing its energy across a much larger area. By the time it reaches the main wall, the energy per unit area is low enough that the hull remains intact. Modern Whipple shields are more sophisticated than the original design. The ISS uses enhanced stuffed Whipple shields that incorporate layers of high-strength fabric, including Kevlar and other ballistic materials, between the outer bumper and the inner hull wall. These intermediate layers further fragment and slow the debris cloud, providing protection against particles up to approximately 1 centimeter in diameter at typical orbital velocities. For a deep space habitat, the Whipple shield principle still applies, but the threat profile is different. In low Earth orbit, the primary concern is orbital debris, fragments of old satellites and rocket stages traveling at relative velocities of 7 to 10 kilometers per second. In deep space, orbital debris does not exist, but natural micrometeoroids are still present, and their velocities relative to a habitat can be higher, particularly if the habitat is traveling at significant speed. The critical issue for a long-duration habitat is not a single impact. It is the cumulative effect of thousands of impacts over years and decades. Each impact removes material from the outer bumper. Over time, the bumper thins, and its ability to fragment incoming particles degrades. The hull itself accumulates microcraters and surface roughening that weaken its structural integrity and degrade the emissivity of any thermal coating applied to its surface. On the ISS, which has more than 2,000 square meters of critical surface area requiring protection, micrometeoroid and debris impacts are a continuous management concern. Windows have been replaced after impacts left visible craters. Solar panels show accumulated pitting damage. Hull surfaces are periodically inspected for damage that might compromise pressure integrity. These inspections and replacements are possible because the ISS is accessible. Spacewalks can be conducted. Replacement panels can be delivered. Damaged sections can be evaluated by engineers on the ground using detailed photographs and sensor data. A deep space habitat has no replacement panels arriving from Earth. A damaged bumper section cannot be swapped out during a routine resupply mission because there are no routine resupply missions. The exterior of the habitat is exposed to the vacuum of space, and any inspection or repair of the outer hull requires an extravehicular activity, which exposes the crew member to the same radiation and micrometeoroid environment they are trying to protect against. Every exterior repair is a risk, and the ability to perform exterior repairs depends on the availability of functional spacesuits, which are themselves complex life support systems with finite operational lifespans. The third external threat is thermal cycling, and it is perhaps the most insidious because it is so quiet. Materials expand when heated and contract when cooled. This is fundamental physics, true of virtually every solid material used in engineering. In deep space, the habitat's thermal environment depends on its orientation relative to distant heat sources, primarily whatever star it is nearest to, and on the internal heat generated by its own systems. If the habitat rotates, different sections of the whole are alternately exposed to and shielded from radiant heat. If the habitat changes its orientation for any reason, navigation adjustments, docking maneuvers, antenna pointing, the thermal profile across its surface changes. Each thermal cycle, each transition from warmer to cooler and back, produces a small amount of mechanical stress in the whole material. The expansion and contraction is tiny, measured in micrometers, but the stress is real, and it concentrates at joints, welds, fastener holes, and any point where two different materials meet, because different materials expand at different rates. A steel bolt in an aluminum fitting, a polymer seal against a titanium frame, a composite panel bonded to a metal structural member. At each of these interfaces, the differential thermal expansion produces stress that the materials must absorb. One cycle is nothing. 100 cycles is nothing. 1,000 cycles is measurable. 10,000 cycles produces microcracks at stress concentration points. 100,000 cycles, which a habitat could easily accumulate over a decade or two, depending on its thermal environment and rotation profile, produces fatigue damage that begins to affect structural integrity. Cracks propagate, seals lose compression, joints develop play. None of this is visible from inside the habitat. It is happening inside the material, at the grain boundary level, beneath the paint and the insulation and the inner hull lining. The crew cannot see it. They may not know it is happening until a pressure sensor detects a slow leak that was not there last month, and the source is traced to a weld in a structural member that has been thermally cycling since the day the habitat launched. These three external threats, radiation, micrometeoroids, and thermal cycling, share a common characteristic that makes them fundamentally different from internal system failures. They cannot be stopped. You can mitigate them, shield against them, design for them, but you cannot turn them off. They are features of the environment, as constant as the vacuum itself. Every second the habitat exists, radiation is penetrating its hull, micrometeoroids are eroding its surface, and thermal cycles are fatiguing its structure. The habitat is under siege, and the siege does not pause, does not negotiate, and does not relent. Now consider what these external threats mean for the internal systems we examined earlier. The water recycling filters that degrade over time are degrading slightly faster because radiation is weakening the polymer membranes they are made of. The seals on the carbon dioxide scrubber valves that stick and lose elasticity are losing elasticity slightly faster because radiation is breaking the molecular chains in the rubber. The reactor control rod mechanism that is developing play in its bearings is developing that play slightly faster because thermal cycling is fatiguing the bearing races. The radiator panels that must shed waste heat are becoming slightly less efficient because micrometeoroid impacts have roughened their surfaces and degraded their thermal coatings. Each of these effects is small. Each one, measured in isolation over a single year, is negligible, But they are not isolated, and they are not measured over a single year. They are simultaneous, they are cumulative, and they compound over the entire operational life of the habitat. The internal degradation rate and the external degradation rate are not separate problems. They are the same problem, seen from two different sides of the whole. And this brings us to the most important limiting factor of all. Not the air system, not the water system, not the reactor. The spare parts. Every physical component in the habitat has a finite operational life. Some components last years, some last decades, some might last longer than the habitat itself if they are never stressed beyond their design limits. But many will not. Filters, seals, bearings, pumps, valves, sensors, circuit boards, lighting elements, motor windings, heat exchanger tubes, catalytic reactor beds. These are the consumable components of the habitat's machinery, the parts that wear out, clog, corrode, fatigue, and eventually fail. At launch, the habitat carries a supply of spares for every critical component. The size of this supply is determined by reliability analysis, a statistical calculation of how many of each component are expected to fail over the planned operational life of the habitat. This analysis is based on failure rate data from similar components used on Earth and in space, adjusted for the specific operating conditions of the habitat. It is an educated estimate, not a guarantee, and it is almost certainly wrong because failure rate data from Earth does not capture the combined effects of the deep space environment. The radiation exposure, the micrometeoroid impacts, the thermal cycling, the absence of gravity or the unusual gravity profile of a rotating habitat, the limited maintenance capability, the absence of manufacturer support. All of these factors alter the real-world failure rates in ways that are difficult to predict and impossible to verify until the habitat is actually operating. The spares inventory might be too large for some components and too small for others. The components that fail first might not be the ones the reliability analysis predicted. In-space manufacturing can extend the supply. Three-dimensional printing technology has been tested on the ISS, producing simple plastic parts from polymer feedstock. More advanced systems capable of printing metal parts are under development. If the habitat carries a capable three-dimensional printer and a supply of raw feedstock materials, it can potentially manufacture replacement parts for some components as needed, rather than carrying pre-made spares for every possible failure. But manufacturing has its own limitations. The printer itself is a machine with moving parts, electronics, and consumables. It requires maintenance. It requires raw materials that are consumed and not easily recycled. It can produce parts of certain geometries and materials, but not all. A printed polymer bracket can replace a broken polymer bracket. A printed metal valve body might replace a corroded valve body if the printer can work with the right alloy and achieve the necessary tolerances. But a replacement electrolysis membrane, a catalytic reactor substrate, a radiation-hardened microprocessor, a high-precision bearing race made of a specific steel alloy with specific heat treatment. These are components that may be beyond the manufacturing capability of anything the habitat can carry. There is a concept that has no official name, but the engineers working on long-duration mission planning understand intuitively. It is the repair horizon. It is the point in time at which the habitat's ability to repair and replace its critical components is exhausted. Not because the crew is incompetent, not because they lack motivation, because the physical resources required for the repairs no longer exist. the last filter of a specific type has been used. The feedstock for the three-dimensional printer is gone. The bearing that needs replacement requires a grade of steel that cannot be fabricated with the equipment on board. The electronic component that failed was the last one in inventory and cannot be manufactured from raw materials by any process available to the crew. At the repair horizon, the habitat does not immediately fail. The crew compensates. They jury-rig. They find workarounds. They accept reduced performance from degraded systems. The water recovery rate drops. The carbon dioxide level rises slightly. The thermal management system works harder to compensate for a radiator that cannot be fully repaired. Each workaround costs something, usually efficiency, sometimes reliability, always margin. The habitat still functions, but it functions with less room for error. The next failure that cannot be repaired is worse than the last one, because the system it affects was already operating at reduced capacity. And the repair horizon is not a single event. It is a rolling front, component by component, system by system, that a habitat crosses the line from maintainable to degrading. The air system reaches its repair horizon first, or the water system, or the power system. It does not matter which one goes first. What matters is that once a critical system crosses that line, the clock begins running on the habitat's ability to sustain life. And the clock does not reset. But spare parts are only half of the repair problem. The other half is knowing what to do with them. And that knowledge, like everything else inside the habitat, is a finite resource that degrades over time. On the ISS, when the water processor developed an unexpected mineral fouling problem that degraded its recovery rate, the crew did not solve the problem alone. Entire engineering teams at NASA's Marshall Space Flight Center spent weeks analyzing the failure, testing alternative chemical formulations in ground laboratories, running simulations, and developing a revised procedure before uploading instructions to the crew. The solution emerged from a distributed network of hundreds of specialists with access to dedicated laboratory facilities, peer review, institutional knowledge spanning decades, and the ability to iterate through failed approaches without risking the crew's water supply during the process. The crew on the station executed the fix. The intellectual work of creating the fix happened on Earth. A deep space habitat cannot access that network. The communication delays we touched on earlier are not just inconveniences for conversation. They are structural barriers to problem solving, and the delay is symmetric. Every question takes that long to arrive, and every answer takes that long to come back. A round-trip conversation with Earth from just 1 light hour away requires a 2-hour gap between asking and hearing. By 2 light hours, the gap is 4 hours. By the time the habitat is a light day from Earth, a single exchange takes 2 full days. This is not a conversation. It is correspondence, and you cannot troubleshoot a failing life support system by letter. The practical consequence is that every unfamiliar failure mode, every problem the crew has not trained for, every chemical reaction or mechanical interaction that was not anticipated in the mission planning, becomes a problem the crew must solve entirely from within. They have documentation, they have manuals, they have recorded procedures and training videos and technical databases. But documentation covers anticipated failures. The failures that threaten a habitat most are the unanticipated ones. The ones that emerge from the specific combination of aging, radiation, contamination, and improvised repairs that no manual was written to address. For those failures, the crew needs not just information, but understanding. The ability to reason from first principles about why a system is behaving the way it is, and what might correct it. And that understanding depends on expertise that is itself a perishable resource. The habitat launched with a crew selected for the breadth and depth of their technical knowledge. The reactor specialist understands nuclear engineering at a professional level. The water systems technician knows fluid chemistry. The agricultural scientist understands soil microbiology and plant physiology. The medical officer can diagnose and treat a wide range of conditions. Together, their expertise covers the full range of systems that the habitat requires. But that expertise is housed in human bodies, and human bodies in deep space are subject to the same slow degradation as everything else aboard. Radiation exposure accumulated over years impairs cognitive function in ways that are subtle but measurable. Reaction times lengthen. Working memory capacity narrows. The ability to hold multiple complex variables in mind simultaneously, exactly the ability that troubleshooting a novel system failure demands, diminishes. Chronic exposure to mildly elevated carbon dioxide, even at levels the crew has grown accustomed to, compounds these effects. The crew does not feel less intelligent, they feel normal, because the change has been so gradual that their baseline has shifted without their awareness. But the person diagnosing a reactor coolant anomaly in year 8 is not operating at the same cognitive level as the person who would have diagnosed it in year 1. They are slightly slower, slightly less flexible in their thinking, slightly more likely to miss a connection or overlook a variable. And expertise does not transfer automatically. If the reactor specialist becomes incapacitated through illness, injury, or the accumulated effects of radiation, the crew does not simply absorb that knowledge from the manuals. The difference between reading a manual and understanding a system well enough to improvise under pressure is the difference between knowing the steps and knowing the reasons behind the steps. A manual tells you what to do when the coolant pressure drops below a threshold. Understanding tells you why the coolant pressure might drop in a way the manual does not describe, and what you might try that is not in any procedure because the situation has never occurred before. That kind of understanding takes years to develop, and in a small crew with no training institution and no outside experts to consult, it can be lost in a single medical emergency. The habitat carries a finite inventory of physical spare parts. It also carries a finite inventory of intellectual spare parts, the expertise distributed across its crew. Both inventories shrink over time. Both are irreplaceable, and when either one is exhausted for a critical system, the result is the same: a failure that cannot be fixed. Not because the will is lacking, but because the means are gone. Biological contamination adds another dimension to this narrowing of margins. The habitat is a closed biological environment. It contains human bodies, food crops, soil or hydroponic media, composting systems, water systems, and air circulation networks. All of these contain microorganisms, bacteria, fungi, and in some cases, viruses. In a well-managed habitat, these microorganisms are part of the life support system. Soil bacteria break down waste and cycle nutrients. Beneficial fungi form symbiotic relationships with plant roots. The human gut microbiome supports digestion and immune function. But microbial communities are not static. They evolve. In a sealed environment with limited genetic influx, the microbial population drifts over time. Species that thrive in the habitat's specific conditions become dominant. Species that do not adapt disappear. Antibiotic-resistant bacteria, which arise naturally through mutation and selection, have a closed environment to colonize without competition from the broader microbial diversity of Earth. If an antibiotic-resistant pathogen establishes itself in the habitat's water system or food production system, the crew's options for treatment are limited to whatever antimicrobial agents they carry and whatever their onboard medical capability allows. Crop diseases present a similar threat. A fungal infection in the wheat crop on Earth is an economic problem. A fungal infection in the wheat crop on a deep space habitat is a food emergency. The crop cannot be replaced from an external source. The growing medium may be contaminated. The fungal spores may have spread to other growing areas through the shared air circulation system. Treating the infection requires antifungal agents, which are consumable supplies and may require destroying the affected crop, which means lost calories that the habitat cannot replace until the next growing cycle, weeks or months away. And there is a deeper problem with the habitat's microbiome that connects to everything else we have discussed. The balance between microbial oxygen consumption and plant oxygen production, the balance that Biosphere 2 got wrong, is not something that is set once and maintained forever. It shifts. Soil microbiome populations change in response to temperature, humidity, nutrient inputs, and the chemical composition of the waste being composted. A shift in microbial activity can alter the rate at which organic matter is decomposed, which alters the rate of carbon dioxide production, which alters the atmospheric composition, which affects plant growth rates, which affects oxygen production. This is a feedback loop, and in a sealed system with limited buffering capacity, feedback loops can amplify small changes into significant ones. The crew may not notice at first. The carbon dioxide scrubber compensates for the slight increase in microbial carbon dioxide production. The atmospheric monitoring system shows readings within normal range, but the scrubber is working harder, consuming its chemical beds faster, and the increased microbial activity is consuming oxygen at a rate slightly above what the plants are producing. Over months, the oxygen level drifts downward by a fraction of a percent, still within tolerance, still safe, but trending in the wrong direction and driven by a biological process that the crew may not fully understand because the soil microbiome is complex and its dynamics are not captured by any sensor they carry. All of these threats, radiation, micrometeoroids, thermal fatigue, spare parts depletion, communication isolation, expertise erosion, biological drift, share a common quality that makes them uniquely dangerous. They are slow. They do not announce themselves with alarms. They do not produce dramatic visible damage. They work beneath the surface at the molecular level, at the microbial level, at the cognitive level, at the statistical level of failure probability. They are the kind of threats that human psychology is worst at recognizing and responding to, because human brains are tuned to notice sudden changes and are remarkably poor at perceiving gradual trends. A crew member who wakes up to a blaring pressure alarm and a visible crack in the hull knows exactly what is happening and responds immediately. A crew member who reviews monthly maintenance logs and notices that the water recovery rate has declined by 0.5% per month for the last 8 months is looking at a trend that may be equally dangerous over time, but does not trigger the same urgency. The alarm tells you to act now. The trend tells you that something is going wrong slowly, and that if you do not identify the cause and correct it, you will eventually face a crisis that you cannot solve because you waited too long. This asymmetry between the speed of degradation and the speed of human perception is one of the deepest challenges of long-duration habitat survival. The habitat does not fail suddenly. It fails slowly. It fails in ways that are difficult to measure, difficult to attribute to a single cause, and difficult to reverse once they have progressed far enough. And the people inside the habitat, the same people who depend on it for every breath, are the ones who must detect, diagnose, and correct these slow failures using only the resources the habitat provides. They must also do this while living inside the machine that is failing, while breathing the air whose composition is drifting, while drinking the water whose purity is declining, while eating the food whose nutritional content may be shifting as the agricultural ecosystem evolves in ways they did not anticipate. Their own health is being affected by the same radiation that is degrading the habitat systems. Their cognitive function may be subtly impaired by elevated carbon dioxide levels they have grown accustomed to. Their judgment may be affected by the chronic stress of living in a confined environment, with the knowledge that every system they depend on is getting older and less reliable. This is not a failure of engineering. The engineers who designed the habitat did the best they could with available technology and knowledge. This is a failure of circumstance. A sealed artificial environment in deep space is subject to entropic forces that no amount of engineering can permanently overcome. Every system degrades, every material ages, every biological community drifts, every mind tires, and the resources to counteract that degradation, whether physical parts or human understanding, are finite, fixed at launch, and shrinking with every repair. The question is not whether this process eventually overwhelms the habitat's ability to compensate. The question is when. And the answer to when depends on a combination of factors that we have not yet fully examined. How the failures stack, how they interact, how the crew responds as the margins narrow and the workarounds multiply, and what it means ultimately when a machine that was designed to imitate a world reaches the point where the imitation begins to break down. That is the final piece of this story, and it is the one that answers the question we started with. Let us not imagine a catastrophe. No meteor punches through the hole. No reactor explodes. No fire sweeps through the oxygen-rich atmosphere of a pressurized module. Those scenarios are dramatic and easy to visualize, and they are not what we are here to talk about tonight. The habitat we have been examining does not die in a moment of violence. It dies the way most complex systems die, slowly, from the inside, through an accumulation of small failures that individually mean nothing and collectively mean everything. Let us watch it happen. It is year 7. The habitat has been operating in deep space for 7 years. By most measures, it is a success. The crew is alive. The air is breathable. The water is drinkable. The crops are growing. The reactor is running. The temperature is stable. If you walk through the corridors, you would see the same functioning environment we described at the beginning of this episode. The lights are on. The ventilation fans hum. The garter trays are green. Someone has taped a new drawing to the common room wall. Life continues. But in the maintenance logs, a different story is taking shape. The primary carbon dioxide scrubber has been operating at 87% efficiency for the last 4 months. One of its 2 zeolite beds has developed a contamination problem that reduces its adsorption capacity, and the crew has not been able to fully restore it because the cleaning procedure requires a solvent they are running low on. The backup scrubber is covering the deficit, but it is now running more hours per day than it was designed for, which means its own components are wearing faster than the maintenance schedule predicted. The water recovery rate, which held at 97% for the first 5 years, has slipped to 93%. The brine processor developed a seal failure 8 months ago. The crew replaced the seal, but the replacement was not an exact match. It is a slightly different polymer, sourced from a general-purpose gasket kit, rather than the specific part designed for the brine processor. It works, but not as well. The processor leaks a small amount of brine into the collection tray, rather than cycling it back through the extraction process. The lost water is measurable. It is being tracked. It is not yet an emergency. One of the 2 redundant coolant pumps in the reactor thermal management loop developed bearing noise in year 5. The crew replaced the bearing using a spare from inventory. The spare was the last one of that size and type. The pump runs smoothly now, but there is no backup bearing available if it fails again. The crew has noted this in the maintenance log, and flagged it for potential 3-dimensional printing from metal feedstock. But the printer has been occupied producing replacement brackets for the agricultural lighting system, which has its own problems. The agricultural lighting system lost 4 of its 36 LED panel arrays in year 6. The panels dimmed gradually over months before failing entirely. Victims of radiation-induced semiconductor degradation. The crew redistributed the remaining panels to prioritize the highest calorie crops, wheat and potatoes, and reduce the growing area for leafy greens. Nutritional variety has narrowed. The crew supplements with stored vitamin tablets, but the vitamin supply is a consumable resource with no replacement source. One of the habitat's 2 spacesuits has a slow leak in its left glove assembly. The crew has patched it twice. It holds pressure for routine inspections, but is no longer rated for extended extravehicular activity. The second suit is functional, but showing wear at the shoulder joint. If both suits become unusable, the crew loses the ability to inspect or repair the exterior hull. None of these problems is a crisis. Every one of them is manageable. The crew has managed them. They have adapted, improvised, and maintained the habitat's essential functions through 7 years of continuous operation in deep space. They are skilled, motivated, and resourceful. But look at the pattern. Every solution they have implemented has cost something. A spare part that cannot be replaced. A system running at reduced efficiency. A backup operating beyond its duty cycle. A growing area reduced. A capability narrowed. The habitat is functional, but is less functional than it was in year 1. And year 8 will be less functional than year 7, because nothing aboard is getting newer. Nothing is being resupplied, and the external environment continues its relentless work of degradation. This is the cascade, not a waterfall, a slow erosion, a landscape of margins that are thinning everywhere at once. In year 9, the cascade begins to accelerate. The backup carbon dioxide scrubber, which has been running above its design duty cycle for 2 years, develops a valve failure. The crew can repair the valve, but the repair requires pulling components from a non-critical atmospheric monitoring system, which means they lose the ability to continuously track trace contaminants in the cabin air. They switch to periodic manual sampling, which takes crew time and provides less frequent data. A slow buildup of a trace contaminant might go unnoticed for days between samples. The reactor coolant pump bearing that was replaced in year 5 begins making noise again. The crew does not have another spare bearing. They attempt to fabricate one using the 3-dimensional metal printer, but the alloy available in feedstock is not identical to the original bearing steel. The printed bearing works, but it is softer. It will wear faster. The crew estimates it might last 2 years rather than the 5-year lifespan of the original. They note this in the log and add the pump to the list of systems on a shortened replacement cycle. The water recovery rate drops to 90%. The brine processor seal that was jury-rigged in year 7 has degraded further. Additionally, one of the filtration beds in the water processor assembly has exhausted its ion exchange capacity. A replacement bed exists in stores, but installing it requires shutting down the water processor for 6 hours, during which the crew must rely on stored reserves. The installation goes smoothly, but the reserve tank level drops noticeably. The crew calculates that at the current rate of water loss, 10% per cycle unrecovered, they are losing approximately 10 litres per day. Over a year, that is 3,650 litres. The habitat launched with reserves sized to buffer losses at 2%, not 10%. At 10% loss, the reserves will be exhausted in approximately 18 months unless the recovery rate is restored. The crew focuses their efforts on the water system. They diagnose the brine processor problem, identify the failing seal, and attempt another replacement. This time, they have no gasket material that is even approximately correct. They fabricate a seal from a section of polymer tubing, heat-formed and pressed into shape. It holds. The recovery rate improves to 94%. Better, but not what it was. The water clock is still running, just more slowly. Meanwhile, the agricultural system absorbs a blow. A fungal infection appears in the potato crop. The infection is identified as a strain of late blight, a disease that has plagued potato farming on Earth for centuries. In the habitat's closed environment, the fungal spores spread quickly through the shared air circulation. The crew isolates the potato growing chamber by sealing its ventilation ducts, but spores have already entered the main air system. 2 of the 3 wheat growing trays show signs of infection within a week. The crew treats the infection with the remaining antifungal agents from the medical stores. The treatment slows the infection, but does not eliminate it. The potato crop is lost. 1 wheat tray is salvaged. The other 2 must be sterilized, their growing media composted and reprocessed, and new seeds planted. The replacement crop will take 3 months to reach harvest. During those 3 months, the crew's caloric intake drops. They ration stored food to bridge the gap. Hunger becomes a daily companion. Physical energy declines. Cognitive function, already subtly affected by mildly elevated carbon dioxide, drops further. Maintenance tasks take longer. Mistakes become more frequent. This is the point in the cascade where the interactions between systems become more dangerous than any individual failure. The crew is tired and hungry. They're spending more time on food system recovery and less time on routine maintenance of other systems. The trace contaminant monitoring that was switched to periodic manual sampling has been delayed because the crew member responsible is occupied with agricultural decontamination. A minor electrical fault in the lighting control system goes unnoticed for 2 weeks because the daily inspection routine has been disrupted. When the fault is finally found, it has caused a small section of wiring insulation to overheat and char, filling the local airspace with acrid smoke that the ventilation system distributes throughout the habitat before the crew can isolate the source. No one is hurt. The fire risk is contained. But the incident cost the crew a day of cleanup and a replacement wiring harness from stores. And the smoke deposits a thin film of soot on surfaces throughout the habitat, including the interior of the ventilation ducts, which will require cleaning over the following weeks to prevent the contaminants from being continuously recirculated. Each of these events is survivable. The crew survives them all. But notice what has happened to the habitat's overall state. In year 1, every system operated at or near its design baseline. Redundancy was intact, spares were plentiful, margins were wide. In year 9, multiple systems are operating at reduced efficiency. Several layers of redundancy have been consumed. Spares are depleted for some critical components. The crew is fatigued, hungry, and stretched thin. The margins that once separated the normal operation from crisis have narrowed to the point where a single additional failure in a critical system could trigger a chain reaction that the crew does not have the resources to stop. The habitat has not failed, but it has lost the ability to absorb failure the way it could in its early years. And in a deep space environment where failures continue to arrive at the same rate they always have, because radiation does not slow down and micrometeoroids do not stop and thermal cycles do not pause, the loss of absorptive capacity is itself a kind of failure. The habitat is still alive, but it is fragile in a way it was not before. One more significant failure, one more crop loss, one more critical component that cannot be replaced, and the cascade reaches a tipping point from which recovery is no longer possible. How long until that tipping point arrives? This is the question at the center of tonight's episode, and the honest answer is that it depends on variables that cannot be precisely predicted. It depends on the quality of the engineering. It depends on the depth of the spares inventory. It depends on the versatility of the manufacturing capability. It depends on the skill and resilience of the crew. It depends on luck, on whether the specific failures that occur happen to affect systems that can be worked around or systems that cannot. But we can bracket the answer using what we know. The ISS has been continuously inhabited since the year 2000. That is over 25 years of continuous operation. But the ISS receives regular resupply, regular maintenance support from the ground, regular delivery of spare parts, and regular crew rotation. It is not a closed system. It is an open system with a lifeline to Earth. Without that lifeline, the ISS would fail within months, not years, because its consumables would be exhausted and its critical components could not be replaced. NASA's target for deep space life support systems, developed in the context of Mars mission planning, is approximately 1,100 days of operation, roughly 3 years, for a crew of 4 to 6 people. This target assumes a high degree of system closure, 98% water recovery, 75% oxygen recovery from carbon dioxide, and a significant but not complete reduction in resupply dependence. It does not assume full independence. It assumes that the mission carries enough consumables and spares to last the duration, with margins for contingency. 3 years is the current engineering horizon for a crewed deep space mission with a defined endpoint. A habitat with no defined endpoint, no return date, no resupply schedule, faces a fundamentally different problem. It must not simply last 3 years, it must last as long as possible, and possible is bounded by the rate at which its systems degrade versus the rate at which they can be repaired. With current or near future technology, a well-designed deep space habitat with comprehensive redundancy, a deep spares inventory, in-space manufacturing capability, and a skilled, well-trained crew could plausibly operate for somewhere between 5 and 20 years before the accumulation of unrepairable degradation begins to compromise core life support functions. The lower end of that range assumes average look with component failures and moderate manufacturing capability. The upper end assumes excellent engineering, extensive spares, a versatile manufacturing system, and a crew that maintains its expertise and cohesion across the entire period. Beyond 20 years, even optimistic projections become speculative. The probability of multiple critical systems reaching their repair horizons simultaneously increases with each passing year. The radiation damage to materials and human health accumulates to levels where both the habitat and its crew are measurably impaired. The microbiome of the habitat has drifted far enough from its initial state that biological life support systems may behave in ways that were not anticipated and cannot be corrected. The crew's institutional knowledge, their understanding of the habitat's systems at the level of principle rather than procedure, may have eroded if the original crew has aged and trained replacements lack the depth of understanding that comes from having built or commissioned the systems themselves. 50 years is almost certainly beyond the reach of any habitat built with technology available today. Not because no individual system could last 50 years, some could. A well-shielded nuclear reactor might run for 50 years with careful management. A pressure hull made of high-quality alloys might maintain structural integrity for 50 years if it avoids significant impact damage. But the web of interconnected systems that creates a livable environment inside that hull, the filters and pumps and seals and sensors and biological processes, that web cannot maintain itself for 5 decades without external input. The consumables run out. The spares are exhausted. The manufacturing capability reaches its limits. The materials degrade beyond repair. A century is not possible, not with anything resembling current technology. The habitat's own materials would be so degraded by radiation, thermal fatigue, and chemical exposure that the structural integrity of the hull itself would be in question. The reactor fuel would be depleted, or the reactor hardware would be beyond maintenance. The biological systems would have evolved into something unrecognizable to the original designers, adapted to the habitat's conditions in ways that might or might not continue to support human life. The idea of a self-sustaining habitat lasting indefinitely is not engineering. It is hope dressed as engineering, and the physics of closed systems does not support it. This is the answer, and it is not the answer most people want to hear. A deep space habitat is not a permanent home. It is a machine with an expiration date. That date is not printed on the hull. It is not a fixed number of years. It is a function of how fast things break and how long they can be fixed, and the math trends in one direction, toward a point where the fixing stops working, where the last spare is used, where the workaround has no workaround, where the margins reach zero, and the next failure, however small, is the one that starts the final decline. There is something important in this answer that goes beyond engineering. It touches on a deeper truth about what we are really talking about when we talk about living in space. On Earth, we live inside a life support system. We just do not think of it that way. The atmosphere provides oxygen and shields us from radiation. The hydrological cycle provides fresh water. The soil provides nutrients for food. The magnetosphere deflects charged particles. The oceans regulate temperature. These systems are so large, so old, so stable relative to human timescales that we experience them not as systems but as conditions. The air is just there. The water is just there. The temperature is just there. We do not maintain them. We do not repair them. We do not think about them at all unless something goes visibly wrong. A deep space habitat strips away this illusion. It forces the inhabitants to confront, every single day, the mechanical reality of their own survival. The air is not just there. It is produced by an electrolysis unit and scrubbed by a zeolite bed. The water is not just there. It is extracted from urine and condensed from exhaled breath. The temperature is not just there. It is managed by a coolant loop and a set of radiator panels that must maintain their surface emissivity, or the whole system drifts out of balance. In a habitat, every comfort is a product. Every breath is manufactured. Every sip of water has passed through a machine. Every calorie was grown under lights that run on electricity from a reactor that runs on fuel that is slowly being consumed. Nothing about the environment is given. Everything about it is made continuously by systems that can break. This is the difference between a place and a machine. A place exists independently of the people in it. A forest is a forest whether anyone walks through it or not. The air above a meadow is breathable whether anyone breathes it. These environments have their own stability, maintained by planetary scale processes that operate without human intervention and have operated for billions of years. A machine exists only as long as it is maintained. A machine that is not serviced degrades. A machine that is not powered stops. A machine that runs out of parts to replace its worn components becomes a static object, no longer performing its function, waiting to be scrapped or forgotten. A deep space habitat is a machine, a profoundly complex, extraordinarily well-designed machine, but a machine nonetheless. And machines do not last forever. The people inside the habitat understand this in a way that no one on Earth ever has to. They understand it not as an abstract principle, but as a lived experience. Every morning they wake up inside a machine. Every task they perform maintains that machine. Every meal they eat was produced by that machine. Every breath they take is the machine's output. And every maintenance report they review tells them, in precise quantitative detail, how much closer the machine is to the point where it can no longer sustain them. This awareness is not something a person can set aside. You cannot forget that the walls holding back the vacuum are degrading. You cannot ignore the maintenance log that shows the water recovery rate declining. You cannot pretend that the spare parts inventory is not shrinking. The knowledge is constant, and it produces a psychological burden that has no equivalent in any environment humans have previously inhabited. On the ISS, astronauts report the comfort of knowing that Earth is right there, 250 miles below, reachable in hours if necessary. On a submarine, sailors know the surface is above them, accessible in minutes. In an Antarctic research station, personnel know that the supply plane will come in spring. A deep space habitat offers none of these psychological anchors. There is no below. There is no surface. There is no spring. There is the habitat, and there is the void. And the distance between rescue and the crew is measured in months or years or forever, depending on how far from Earth the habitat is located. The communication delay compounds this isolation. A crew member who discovers a critical system failure and sends a distress message to Earth will wait hours days or years for response, depending on the habitat's distance. The response, when it arrives, will be advice, not physical help. No spare part will be launched. No repair crew will be dispatched. No evacuation vehicle will dock. The crew is alone with the problem, alone with the machine, alone with the knowledge that every solution must come from within the hull. This psychological reality interacts with the physical reality of system degradation in a way that makes both worse. A stressed, tired, hungry crew makes more maintenance errors. Errors accelerate degradation. Accelerated degradation increases stress. The loop feeds itself. The habitat's physical state and the crew's psychological state are coupled systems, each one affecting the other, and in a declining habitat, both tend to decline together. We started tonight inside a habitat that looked like a home. The lights were warm, the air was clean, the garden was green. Someone had pinned a photograph to the wall. It felt safe. It felt like a place where people could live. And people can live there, for a time. The engineering is real. The systems work. The habitat does sustain life. It does hold back the vacuum. It does produce breathable air and drinkable water and edible food. It does regulate temperature and manage waste and generate power. All of these things are achievements of extraordinary human ingenuity, representing decades of research and development and the accumulated knowledge of thousands of engineers and scientists. But the habitat is not a world. It is a simulation of a world, running on hardware that ages, powered by fuel that depletes, maintained with parts that run out. Earth does not need maintenance. Earth's atmosphere regenerates itself through planetary scale cycles that have operated for billions of years. Earth's water cycle is driven by the energy of the sun falling on an ocean surface that covers 70% of the planet. Earth's soil is the product of geological and biological processes spanning millions of years, maintained by ecosystems of staggering complexity and resilience. These systems do not have spare parts because they do not have parts. They are not machines. They are processes, emergent properties of a planetary body that has been running its own chemistry for 4.5 billion years. A habitat tries to replicate in miniature inside a metal shell what a planet does naturally at a scale that dwarfs comprehension. And it cannot. Not indefinitely. The miniature version lacks the buffers, the redundancy, the sheer scale of material and energy reserves that a planet provides. On Earth, if one forest burns, another forest absorbs the excess carbon dioxide. If one species declines, others fill the ecological niche. The planetary system has billions of years of accumulated resilience, tested by asteroid impacts and ice ages and supervolcano eruptions. And it recovered from all of them because it had the mass, the energy, and the time to do so. A habitat has none of that. Its buffers are measured in liters and kilograms, not in oceans and continents. Its energy reserve is a reactor, not a star. Its ecological resilience is a few trays of crops and a composting bin, not a biosphere with millions of species and billions of tons of biomass. When something goes wrong in the habitat, the margin for recovery is thin. When multiple things go wrong at once, the margin may not exist at all. This is not a reason to stop building habitats. It is not a reason to abandon the idea of human presence in deep space. It is a reason to be honest about what habitats are and what they are not. A habitat is a tool, a temporary shelter, a bridge between departure and arrival. It is not a destination in itself. It is not a replacement for a world. It is the machine you build because you do not yet have a world to stand on. And you need something to keep you alive until you find one or build one or grow one from the raw materials of an alien landscape. The people who design habitats know this. The engineers at NASA and ESA who work on deep space life support systems know that they are designing machines with finite lifespans, not permanent dwellings. The challenge they wrestle with every day is how to extend that lifespan, how to push the repair horizon further out, how to make the machine more resilient, more repairable, more forgiving of the small failures that will inevitably accumulate. They know that the question is not whether the habitat will eventually fail. The question is whether it will last long enough to accomplish whatever mission it was built to support, and that reframing matters. A habitat does not need to last forever. It needs to last long enough for the crew to reach their destination, long enough for the research to be completed, long enough for the colony on the surface to become self-sufficient, long enough for the next ship to arrive with fresh supplies and replacement parts. The habitat is not the goal, it is the means, and understanding its limitations honestly is not pessimism. It is the prerequisite for using it wisely. Tonight, we asked how long a space habitat could really survive in deep space. The answer is this: a habitat survives as long as every critical system remains repairable, powered, sealed, and balanced. In deep space, without resupply, without rescue, without the vast buffering capacity of a planetary environment, the true limit is not one catastrophic failure. It is the slow accumulation of tiny system losses, each one shaving a margin, each one consuming a resource, each one narrowing the space between survival and collapse. The habitat does not explode. It does not crack open in a dramatic breach. It slowly, quietly, imperceptibly loses the ability to correct itself. The air gets a little harder to produce. The water gets a little harder to clean. The temperature gets a little harder to control. The crops yield a little less. The repairs take a little longer. And one day, the people inside look around at the walls that have kept them alive and realize that the machine that has been imitating a world for them has reached the limit of its imitation. The lights are still on. The fans still hum. The garden trays still hold green things, but the margins are gone. The spares are gone. The workarounds have been exhausted. And the void outside, patient and absolute, is no longer being held back by a functioning system. It is being held back by a system that is trying and failing to remain one. In deep space, a habitat is not a home. It is a machine pretending to be a world. And every machine, no matter how brilliantly designed, no matter how carefully maintained, eventually reaches the moment where the pretending stops. That is the truth the stars do not tell you when you look up and dream about living among them. The distance is not the hardest part. The hardest part is that when you arrive, wherever you arrive, you are still inside a machine, and the machine is counting down. Good night.